Right now, somewhere in the darkness between stars, invisible predators drift through our galaxy. They have no light, no sound, no warning of their approach. And if one passed close enough to our solar system, we wouldn't see it coming until it was far too late. These are rogue black holes. Stellar corpses torn from their birthplaces, now wandering the Milky Way in complete silence. Scientists estimate there could be hundreds of millions of them out there, and we've barely detected a handful. The rest remain hidden, moving through space like cosmic ghosts, bending light around themselves, swallowing anything that crosses their path. What makes them truly terrifying isn't just their power. It's that we have almost no way to track them until they're already here. And when astronomers finally developed methods to spot these wanderers, what they found was deeply unsettling. Black holes form when massive stars collapse. We've known this for decades. A star 20 times the mass of our sun burns through its fuel, its core implodes, and gravity crushes everything into a point of infinite density. What's left behind is an object so dense that not even light can escape its pull. Most of these black holes stay where they formed, anchored in place by the remnants of their stellar neighborhood. But not all of them. When a massive star explodes as a supernova, the blast isn't always symmetrical. If the explosion throws more material in one direction than another, the newborn black hole gets kicked hard. Astronomers call these natal kicks, and they can launch a black hole across the galaxy at speeds exceeding 600 kilometers per second. That's more than 2 million kilometers per hour. Fast enough to escape the gravitational grip of its birthplace entirely. Once free, these objects become nomads. They don't orbit anything. They don't belong to any star system. They simply drift through the galaxy, following trajectories set by that violent birth moment, invisible and utterly indifferent to whatever lies in their path. Here's where it gets worse. Our galaxy has been forming stars for over 13 billion years. Millions of massive stars have lived and died in that time. Each one that met the right conditions created a black hole. And a significant fraction of those black holes received kicks strong enough to send them wandering. Do the math, and you arrive at a disturbing conclusion. The Milky Way should be filled with these things. Early estimates suggested tens of millions. More recent models push that number higher, potentially into the hundreds of millions. Picture that for a moment. Between 100 million and 400 million rogue black holes, drifting silently through the same space we occupy. Most are stellar mass black holes, between 5 and 50 times the mass of our Sun. Small by cosmic standards, but devastating by any measure that matters to us. And we can't see them. A black hole by definition emits no light. It's a hole in space where light goes to die. The only way we typically detect black holes is by watching how they affect their surroundings. If a black hole is pulling gas from a companion star, that gas heats up as it spirals inward, glowing brilliantly in X-rays before it vanishes beyond the event horizon. Binary systems like this are relatively easy to spot. We've cataloged dozens of them. But a rogue black hole traveling alone through empty space has nothing to feed on. No companion star. No accretion disk. No telltale X-ray signature. It's just a gravitational knot in the fabric of spacetime, moving silently through the void. For decades, astronomers assumed these objects were essentially undetectable. They were out there, sure, but finding them seemed impossible. Then someone realized we'd been thinking about the problem wrong. Even invisible objects reveal themselves through gravity. Einstein showed us this more than a century ago. Mass warps spacetime, and light follows those curves. When light from a distant star passes near a massive object, the object's gravity bends that light like a lens. If the alignment is precise enough, the background star appears to brighten temporarily as its light is magnified and focused toward us. Astronomers call this gravitational microlensing. The technique had been used successfully to find planets, distant stars, even other black holes in binary systems. But using it to hunt lone rogue black holes required a different approach entirely. You'd need to monitor millions of stars continuously, waiting for one to brighten in exactly the right way. The chances of catching such an event are microscopically small. The alignment has to be perfect, the timing has to be right, and you have to be watching that exact star at that exact moment. In 2011, a team of astronomers decided to try anyway. They pointed their telescopes toward the galactic bulge, the dense central region of the Milky Way where stars are packed close together. More stars mean more opportunities for alignment. They monitored the brightness of millions of stars simultaneously, searching for the characteristic signature of a black hole passing in front of them. For years, they found nothing conclusive. Hundreds of microlensing events, yes, but most could be explained by normal stars or brown dwarfs. Then in 2022, they announced something different. An event designated MOA-2011-BLG-191. The light curve was perfect. A star had brightened over several weeks, peaked, then faded back to normal. But the duration and shape of that brightening suggested something unusual. The lensing object wasn't a star. It was too massive and too dark. After ruling out other possibilities, the team concluded they detected a rogue black hole. Somewhere between 2 and 7 solar masses, drifting alone through the galaxy approximately 5,000 light-years from Earth. It had passed directly between us and a background star, briefly magnifying that star's light before continuing on its silent journey. This was the first time anyone had definitively detected an isolated black hole wandering through space. Not orbiting anything. Not feeding on anything. Just moving. And it raised an immediate question. If we found one, how many more are out there that we haven't found? The galaxy is enormous. 300 billion stars spread across 100,000 light-years. Even hundreds of millions of rogue black holes would be sparse in that volume. The chances of one passing close to any particular star are vanishingly small. But close is a relative term in space. A black hole doesn't need to hit something directly to affect it. Gravity works at a distance. If a rogue black hole passed within a few light-years of our solar system, we'd likely never notice. It would tug slightly on the orbits of distant comets in the Oort cloud, maybe nudge a few toward the inner solar system, but nothing catastrophic. Pass within 1 light-year, and the effects become more pronounced. Orbits destabilize. Long-period comets get redirected. The delicate gravitational balance that keeps our solar system stable starts to shift. Get closer than that, and things deteriorate rapidly. A black hole passing within the orbit of Neptune would gravitationally scatter the outer planets. Jupiter's orbit would shift. Saturn's rings might destabilize. The asteroid belt could be stirred into chaos, sending rocks careening through the inner solar system. Earth's orbit would change. Not immediately, not catastrophically in human terms, but enough to alter our climate over centuries. Enough to make our world unrecognizable. And if one passed within the orbit of Mars, we'd have months at best. Maybe weeks. The sun itself would be affected, its outer layers potentially stripped away as the black hole's gravity pulled at stellar material. Earth's orbit would become wildly elliptical or be ejected from the solar system entirely, flung into interstellar space to freeze in the darkness. The worst part isn't the destruction itself. It's the warning time. Or rather, the complete lack of it. Current detection methods only work when a rogue black hole passes directly in front of a background star from our perspective. By the time we detect that microlensing event, we're observing something that happened years or centuries ago, depending on the distance. The light we're seeing left that region of space long before we started watching. The black hole itself is already somewhere else entirely, continuing its journey along a path we can't predict. We have no early warning system. No way to scan ahead and spot an approaching threat. Gravitational wave detectors like LIGO can detect black hole mergers halfway across the universe, but a single black hole drifting through space produces no gravitational waves. It's silent on every wavelength we can measure, visible only through the brief distortion it causes when perfectly aligned with a distant light source. Astronomers are working on better detection methods. Upcoming surveys will monitor more stars more continuously, increasing the chances of catching microlensing events. The Vera Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every few nights, watching for anything that changes. That includes the subtle brightening caused by gravitational lensing. But even with better surveys, we're still looking at a reactive system. We find these objects after they've already passed, not before. And the galaxy is simply too large, too dark, too filled with empty space to monitor comprehensively. The number of rogue black holes out there almost certainly exceeds our ability to track them all. Which brings us to an uncomfortable probability calculation. With hundreds of millions of these objects wandering the Milky Way, and 13 billion years of galactic history behind us, what are the chances one has already passed close to our solar system? Or that one will in the future? The distances involved are staggering enough that the risk to any individual star system remains low over human timescales. But over millions of years, over billions, the odds shift considerably. And we're not just talking about direct hits. Even a distant passage could destabilize the Oort cloud, sending comets plunging toward the inner planets. Some researchers have suggested that periodic comet bombardments in Earth's history might be explained by exactly this mechanism. A rogue black hole passing through the outer solar system every few tens of millions of years, stirring up frozen debris and sending it inward. It's speculative, but it fits certain patterns in the geological record. And it suggests these invisible wanderers have been influencing our corner of space far longer than we've been here to notice. The galaxy's structure offers little comfort when you consider the mechanics. Rogue black holes don't travel in neat, predictable orbits like planets around a star. They follow paths determined by countless gravitational interactions over billions of years. A close encounter with another star system deflects the trajectory. Passage through a dense molecular cloud changes the velocity. The cumulative effect of these interactions creates something closer to a random walk than an orbital pattern. Which means prediction becomes functionally impossible beyond a certain distance. What makes this particularly unsettling is scale. We think of black holes as massive objects, and compared to everyday experience, they are. But in galactic terms, a stellar mass black hole is microscopic. The event horizon of a 10 solar mass black hole measures roughly 60 kilometers across. That's smaller than many cities. Now imagine trying to spot something that size, something that emits no light, against the backdrop of a galaxy 100,000 light-years in diameter. You're looking for a dark marble in an ocean at night. From another continent. The only reason we've detected any at all is because space isn't completely empty. Gas and dust exist between stars, thin beyond anything we'd call a vacuum on Earth, but present nonetheless. When a black hole moves through this tenuous material, it pulls some of it inward. That gas heats up through friction and compression, reaching temperatures where it emits X-rays. Not much. Not the brilliant accretion disks we see around supermassive black holes in galactic centers. Just a faint glow, barely detectable even with our most sensitive instruments. But here's the problem with using that detection method. It only works if the black hole happens to be passing through a region with enough gas to produce a visible signature. Most of interstellar space is far emptier than that. A black hole could pass within a light year of Earth, close enough to potentially affect the orbits of outer solar system objects, and we'd see nothing. No X-rays. No visible light. No radio emissions. Just gravitational effects we wouldn't notice until something started behaving strangely. The math on close approaches is genuinely disturbing. Researchers have calculated that a black hole passing within 50 astronomical units of the Sun, roughly the distance to the Kuiper belt, would disrupt the orbits of trans-Neptunian objects significantly. Within 20 astronomical units, orbital perturbations would extend to the giant planets. Closer than 10, and Earth's orbit itself becomes unstable over timescales ranging from centuries to millennia, depending on the exact trajectory and mass involved. These aren't extinction-level events in the immediate sense. The black hole doesn't need to hit us to cause catastrophic problems. Orbital changes of even a few percent would alter Earth's climate dramatically. Seasons would shift. The length of the year would change. If the orbit became more elliptical, we'd experience temperature swings between perihelion and aphelion far more extreme than current seasonal variations. Glaciation cycles would accelerate or halt entirely. Ocean currents would reorganize. Weather patterns would transform beyond recognition. Life on Earth has survived worse. Mass extinctions punctuate the fossil record, some far more severe than what an orbital disruption might cause. But those events unfolded over thousands or millions of years. Ecosystems had time to migrate, adapt, or collapse gradually. A black hole passage could destabilize things within decades. Too fast for agricultural systems to adjust. Too fast for species to migrate to new climate zones. Too fast for human civilization to reorganize around new realities. The truly nightmarish scenarios involve closer approaches. If a rogue black hole entered the inner solar system, say within Mars's orbit, the effects would be immediate and overwhelming. Earth's orbit wouldn't just shift slightly. It would change fundamentally. We might be ejected from the solar system entirely, flung into interstellar space along a trajectory determined by the exact angle and speed of the encounter. Or we might fall inward, spiraling toward the Sun over a timescale of centuries. Either way, Earth as a habitable planet would end. Ejection means freezing. Without the Sun's heat, surface temperatures would plummet to near absolute zero within years. The atmosphere would condense and freeze, falling as snow that would eventually cover the entire surface in a layer hundreds of meters thick. Oceans would freeze solid to their beds. Any life that survived would exist in deep subsurface environments, perhaps around geothermal vents, living off Earth's internal heat rather than solar energy. Human survival would require either impossible engineering or simply wouldn't happen. Falling inward carries its own horror. The journey toward the Sun would take time, but the end result is incineration. Earth's orbit decaying, bringing us closer to a heat source that already makes the equator brutal during summer. Temperatures would rise steadily. Oceans would boil away. The atmosphere would be stripped by solar wind. Eventually, the planet would be torn apart by tidal forces before ever reaching the solar surface, debris scattered across the inner solar system like a planetary corpse. The galaxy doesn't care about any of this. These events occur with statistical regularity across billions of star systems. Most stars will experience close encounters with rogue objects over their lifetimes. Some will be disrupted. Some will capture new planets or have existing ones stripped away. It's part of the normal evolution of galactic structure. We just happen to be conscious observers existing during a period when our particular star system hasn't experienced such an event recently. Recently, in this context, means within the last few 100 million years. The geological record shows no evidence of sudden orbital disruptions on that timescale. Earth's climate has varied, sometimes dramatically, but always within ranges consistent with predictable astronomical cycles. The Milankovitch cycles that drive ice ages operate over tens of thousands of years and result from subtle variations in Earth's orbital eccentricity and axial tilt. Not the kind of violent perturbations a black hole passage would cause. But absence of evidence isn't evidence of absence over longer timescales. Go back far enough, and the record becomes unclear. The early solar system was chaotic. Planets migrated. Giant impacts occurred. The late heavy bombardment around 4 billion years ago reshaped the inner solar system. Could some of that chaos have been influenced by a passing rogue black hole? Possibly. We have no way to determine that from current evidence. The gravitational signatures would have been erased long ago by subsequent evolution. What we can determine is frequency based on what we observe elsewhere. Studies of stellar velocities in our galactic neighborhood show occasional stars moving at speeds inconsistent with normal orbital patterns. Hypervelocity stars, traveling fast enough to escape the galaxy entirely. Some of these gained their speed through close encounters with the supermassive black hole at the galactic center. Others might have been accelerated by interactions with rogue black holes in the disk. The distribution of these fast-moving stars gives us clues about how often such encounters occur. The numbers suggest a close approach between a rogue black hole and a random star system happens perhaps once every few 100 million years within any given volume of space. That sounds reassuring until you remember we're talking about an entire galaxy containing hundreds of billions of stars. Multiply that out, and you get thousands of these encounters happening somewhere in the Milky Way right now. This moment. As you process these words, a black hole is likely disrupting a solar system dozens or hundreds of light years away. We'll never see it. Never detect it. Never know which star just had its planetary system torn apart. The speed at which these objects move creates additional problems for detection. Stellar velocities in our region of the galaxy average around 200 kilometers per second relative to the local standard of rest. A rogue black hole might be moving faster or slower, depending on its history, but it's in that general range. At those speeds, an object crosses 1 astronomical unit, the distance from Earth to the Sun, in about 2 months. It could traverse the entire solar system in less than a year. Detection, analysis, and response would need to happen within that window. Except we can't detect them reliably in the first place. And even if we could, what response exists? You can't deflect a black hole. You can't destroy it. You can't negotiate with fundamental physics. The only option would be evacuation, and evacuating Earth's population to somewhere safer runs into the obvious problem that there is nowhere safer within reach. Generation ships heading to other star systems would take thousands of years to reach destinations that might themselves be threatened by rogue black holes. Underground bunkers might preserve some fraction of humanity through orbital disruption, depending on severity, but only if Earth remains in a relatively stable orbit around the Sun. Ejection into interstellar space makes that impossible. The planet becomes uninhabitable too quickly for any bunker to matter. This is the situation we exist within. A galaxy filled with invisible threats following unpredictable paths at velocities that leave no time for meaningful response. The odds of a direct impact remain low over human timescales. Low enough that it doesn't make sense to lose sleep over it specifically. But the odds of an encounter somewhere in our cosmic neighborhood, close enough to affect our understanding of how stable planetary systems really are, sit much higher. The question becomes what kind of encounter would actually matter to us. Not just theoretically, but in ways we could measure or experience within human lifetimes. Start with gravitational influence at a distance. A stellar mass black hole passing within a few light years of the solar system wouldn't cause immediate catastrophe, but it would perturb the Oort cloud. That's the spherical shell of icy bodies extending roughly halfway to the nearest star, loosely bound to the Sun's gravity. Disturb that region, and you send comets falling inward toward the inner solar system. Not immediately. The journey takes thousands to millions of years depending on initial position and velocity. But once started, the process continues regardless of whether the black hole remains nearby. Historical impact records on Earth and the Moon show periodic increases in cratering rates. Some researchers have proposed these patterns correlate with the solar system's oscillation through the galactic plane, where stellar density runs higher. More stars means more gravitational perturbations. More perturbations means more comets get nudged loose. The mechanism makes sense even if the specific correlations remain debated. A rogue black hole passing through the Oort cloud would produce similar effects, just concentrated in time rather than spread across millions of years of gradual oscillation. The increased impact rate wouldn't sterilize Earth. Life has survived multiple impact events far worse than anything a perturbed Oort cloud could produce. But it would stress ecosystems, potentially triggering extinctions among larger organisms less able to shelter or adapt quickly. Human civilization, dependent on stable agriculture and infrastructure, would face serious challenges. Not extinction level, but enough to reshape societies and potentially set back technological development by centuries. That scenario assumes the black hole stays several light years away. Move it closer and effects intensify. At 1 light year out, roughly a quarter of the distance to Proxima Centauri, gravitational effects become more direct. The outer planets would experience measurable orbital perturbations. Nothing dramatic over human timescales, but enough to show up in precision tracking data. Jupiter's orbit might shift by fractions of a percent. Saturn's rings could develop new gaps or resonances as orbital periods change slightly. These aren't catastrophic alterations, but they'd be detectable, and they'd tell us something massive had passed nearby. The inner solar system would feel weaker effects at that distance. Earth's orbit wouldn't change noticeably within a single human lifetime. But over centuries, small perturbations accumulate. Climate patterns depend partly on Earth's orbital eccentricity and axial tilt. Alter those parameters even slightly and you change how solar energy distributes across the planet's surface. Ice ages have been triggered by orbital variations smaller than what a passing black hole at 1 light year might induce. Now bring it closer still. Half a light year. A tenth. At these ranges, we're talking about an object whose gravitational influence begins competing with the Sun's hold on the outer planets. Neptune and Uranus could experience significant orbital changes within decades. Their moons might be stripped away entirely, sent tumbling into new orbits around the Sun or ejected into interstellar space. The inner solar system would still remain relatively protected by distance and the sun's stronger local gravity, but relatively does heavy lifting in that sentence. At a tenth of a light year, maybe 3 months of travel time at typical stellar velocities, detection becomes theoretically possible through gravitational lensing. The black hole's gravity would bend light from background stars, creating a characteristic pattern of brightening and positional shifts as it moves across the sky. Dedicated surveys searching for such events could potentially spot it, given enough luck in the right observational geometry. But that requires the black hole to pass almost directly between us and cataloged background stars, and it requires astronomers to be looking at the right patch of sky at the right time with equipment sensitive enough to catch subtle lensing signatures. The odds aren't favorable. Even if detected, the warning time measured in months doesn't allow for much beyond observation and calculation. We'd watch it approach, model its trajectory, estimate its mass based on lensing strength, and project what effects it might have on planetary orbits. Then we'd wait to see if the models were right. If the black hole passes within the outer solar system itself, within Neptune's orbit, we've moved from theoretical concern to immediate crisis. At those ranges, orbital mechanics become chaotic in the technical sense. Small changes in initial conditions produce wildly different outcomes. Whether Earth remains in a stable orbit or gets perturbed into a more elliptical path, whether the perturbation is mild or severe, whether we end up closer to the Sun or farther away, all of this becomes sensitive to precise details of the black hole's mass, velocity, and trajectory. Run the simulation 1,000 times with slightly different starting parameters and you get 1,000 different results. Some show minimal impact. Others show Earth's orbit elongating enough to create extreme seasonal temperature swings. A few show ejection from the solar system entirely. The disturbing part isn't that ejection scenarios exist. It's that we couldn't predict which outcome would occur until the black hole was already here, moving through the system, its gravity actively reshaping orbital paths in real time. By then it's far too late for any response beyond documentation. Consider what ejection actually means. Earth doesn't crash into the black hole. It doesn't get torn apart by tidal forces unless the approach is extraordinarily close, within a few million kilometers. What happens instead is the planet gets gravitationally kicked, like a billiard ball struck at an angle. The velocity change might be only a few kilometers per second, but that's enough. Earth's orbital velocity around the Sun sits at about 30 kilometers per second. Add or subtract even a small fraction of that and you change whether the orbit remains bound to the Sun. Once unbound, Earth drifts into interstellar space. The Sun shrinks to just another bright star in the sky, eventually indistinguishable from the others except by position. Surface temperatures drop rapidly as solar heating cuts off. Oceans freeze within years. The atmosphere begins condensing as temperatures fall below the freezing points of various gases. Carbon dioxide snow falls first, then nitrogen, then oxygen. Eventually you're left with a ball of ice-coated and frozen air, drifting through the void at several dozen kilometers per second relative to the galactic frame. Deep underground, residual heat from radioactive decay in Earth's core continues for billions of years. Hypothetically, life could persist in deep crustal environments or around hydrothermal vents on the ocean floor, sealed beneath kilometers of ice. These ecosystems already exist in darkness, independent of photosynthesis, powered by chemical energy from the planet's interior. They might not even notice the Sun's absence, at least not immediately. Surface life ends completely. Everything dependent on solar energy, which means everything humans need to survive, ceases functioning within months. No agriculture. No renewable energy. No ecosystem services. Survival would require moving underground with nuclear or geothermal power, growing food under artificial light, and maintaining sealed habitats indefinitely. The technical challenges are immense but theoretically solvable. What's not solvable is doing this for billions of people with no preparation time. Even if a fraction of humanity survived in deep bunkers or sealed cities, you've essentially ended human civilization as we understand it. The survivors would live in permanent artificial environments, cut off from any natural world, maintaining themselves through technology that must never fail because there's no outside to escape to. This is assuming the ejection is gentle enough to leave Earth intact as a physical body. A closer approach could generate tidal forces strong enough to cause massive earthquakes, trigger volcanic eruptions, or in extreme cases, literally crack the planet's crust. The threshold for tidal disruption depends on how close the black hole passes and how fast. A stellar mass black hole would need to come within a few 100,000 kilometers to tear Earth apart through tidal forces alone. That's close, closer than the Moon's orbit. It's unlikely but not impossible. What's more likely, if a rogue black hole passes through the inner solar system at all, is significant orbital disruption without physical destruction. Earth survives as a planet but ends up somewhere it wasn't before, in an orbit that no longer supports the climate patterns civilization developed around. Maybe the new orbit is more elliptical, creating extreme seasonal variations. Maybe it's slightly closer to the sun, triggering runaway greenhouse effects. Maybe it's farther out, pushing the planet toward permanent glaciation. Each scenario creates different challenges, some potentially manageable with advanced technology, others not. The fundamental problem remains unchanged. We can't predict these events with useful lead time. We can't prevent them. We can barely detect the objects responsible. And the consequences range from inconvenient to civilization ending depending on variables we can't control. So we exist in a galaxy where these objects drift through the dark, occasionally reshaping solar systems they pass near, and we have no systematic way of knowing where they are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance doesn't mean ignoring the problem. It means acknowledging what we can and can't control, and focusing effort on the things that actually matter within our capability to influence. This brings us to something slightly more optimistic but equally strange. What happens if we reverse the scenario? Instead of losing the sun, what if Earth captured a second one? Binary star systems are common in the galaxy. Roughly half of all stellar systems contain two or more stars orbiting each other. If our solar system encountered a wandering star under precisely the right conditions, gravitational interactions could theoretically bind it into a stable configuration. The newcomer would need exactly the right mass, velocity, and trajectory. Too fast, and it simply passes through. Too slow or too close, and orbital chaos follows. Let's assume the best case. A star roughly half the sun's mass approaches from a perpendicular angle to the solar system's plane, moving at just the right speed to be captured into a wide elliptical orbit. The two stars settle into a configuration where they orbit their common center of mass every few thousand years, staying far enough apart that planetary orbits remain mostly stable. Even in this ideal scenario, everything changes. First, there's no longer a single point in the sky that defines day and night, seasons, or climate stability. Depending on orbital positions, Earth might receive varying amounts of total radiation throughout the year. When both stars align on the same side, the planet gets hotter. When they oppose each other, one might be visible during what used to be night, eliminating true darkness for months at a time. Ecosystems evolved under predictable light cycles would face immediate stress. Plants time their growth, flowering, and dormancy to seasonal patterns that have remained consistent for millions of years. Disrupting that rhythm doesn't just inconvenience agriculture. It destabilizes the foundation of terrestrial food webs. Animals navigate, hunt, and reproduce based on day length and seasonal cues. Migratory birds use the sun's position for orientation. Nocturnal species depend on darkness. Coral reefs synchronize spawning to lunar cycles and water temperature patterns tied to solar radiation. All of these systems assume one sun following a predictable path. The climate effects cascade through every layer of atmosphere and ocean. Earth's climate system relies on differential heating between equator and poles to drive atmospheric circulation and ocean currents. Those patterns exist because solar radiation arrives at different angles across latitudes and varies predictably through the year. Adding a second star, even one much dimmer than the sun, introduces new heating patterns that don't align with the geography. Jet streams might shift latitude or weaken entirely. Ocean currents that distribute heat globally could alter course or speed. The intertropical convergence zone, which drives tropical weather patterns, might oscillate unpredictably or split into multiple bands. Then there's orbital mechanics. Even if Earth's orbit remains stable initially, long-term gravitational perturbations from the second star would accumulate. Over thousands of years, Earth's orbital eccentricity might increase, creating more extreme seasonal variations. The axial tilt that currently gives us moderate seasons could begin precessing faster or shifting to new angles. Other planets face worse outcomes. Mars, already in a precarious position with thin atmosphere and marginal temperatures, could be pushed into an orbit that makes it even less habitable. Jupiter and Saturn, the solar system's gravitational anchors, would experience altered orbits that ripple through the entire planetary arrangement. The asteroid belt, currently stable in gaps maintained by Jupiter's gravity, could destabilize. Resonances that previously kept asteroids in safe orbits might break down, sending debris inward toward the inner planets. Impact rates could increase significantly over geological timescales. None of this happens overnight. A captured star doesn't immediately scramble planetary orbits. The changes unfold over decades, centuries, millennia. But they're directional. The solar system wouldn't settle into a new stable state identical to the old one. It would transition toward a different equilibrium, one that might not include Earth in the habitable zone. From a human perspective, even the short-term effects present serious challenges. Agriculture depends on predictable growing seasons. Water resources rely on consistent precipitation patterns driven by stable atmospheric circulation. Infrastructure assumes certain temperature ranges and weather extremes. All of that gets recalibrated when the fundamental energy input to the climate system becomes variable. And we're still assuming the best case where the second star approaches gently and settles into a distant orbit. More likely scenarios involve closer approaches that don't result in capture but still perturb planetary orbit significantly during the encounter. A star passing through the outer solar system would gravitationally scatter comets from the Oort cloud, sending them falling inward. Some would miss Earth. Some wouldn't. The impact risk would spike for thousands of years after the encounter as these disturbed objects crossed the inner system. Planetary orbits themselves could shift. Not dramatically, not instantly, but enough to matter. Earth might end up in a slightly wider orbit, reducing solar radiation and triggering gradual cooling. Or a slightly tighter orbit, increasing temperatures and accelerating ice melt. Either direction creates a planet humans didn't evolve on and haven't built civilization around. The probability of capturing a second star remains extremely low. Space is vast, stellar encounters are rare, and the specific conditions needed for stable capture are narrow. But stellar flybys, close enough to disrupt things without capture, occur more frequently on geological timescales. The Sun will experience multiple close encounters with other stars over its remaining lifespan. Most will pass without incident. Some won't. And this assumes we're only dealing with normal stars. What if the intruder is a white dwarf, a stellar remnant much smaller but incredibly dense? Or a neutron star, packing more mass than the Sun into a sphere 20 kilometers across? The gravitational effects scale with mass, not volume. A neutron star passing through the outer solar system would wreak havoc despite being physically tiny. These objects are harder to detect at distance because they emit little light. A white dwarf shines dimly. A neutron star barely radiates in visible wavelengths. By the time we noticed one approaching, it might be too late to do anything beyond calculating the consequences. The galaxy contains billions of stellar remnants drifting through interstellar space. Most are isolated, moving on predictable paths that won't intersect our neighborhood. But on timescales of millions or billions of years, encounters become statistically inevitable. The solar system will interact with other massive objects. The question isn't if, but when and how severely. We can model these scenarios mathematically. We can run simulations showing what happens to planetary orbits under various perturbations. We can calculate impact probabilities and climate shifts. What we can't do is prevent them or predict them far enough in advance to matter. That leaves us in an odd position. We understand the risks. We know the mechanisms. We can describe in detail what would happen under different conditions. But we can't defend against threats operating at stellar scales with energies and masses that make human technology irrelevant. This isn't fatalism. It's recognition that some problems exist outside our ability to solve. You don't build contingency plans for events that would end technological civilization because there's no point. Either the event doesn't happen and the planning was unnecessary, or it does happen and the plans don't help. What matters instead is understanding our place in a dynamic galaxy where stability is temporary and change is guaranteed. The solar system occupies its current configuration because nothing has disturbed it recently. That's not a permanent state. It's a snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. The Sun formed 4.6 billion years ago from a collapsing molecular cloud. It will continue fusing hydrogen for another 5 billion years before exhausting its core fuel and expanding into a red giant. Within that time span, the solar system will experience multiple gravitational encounters with passing stars, clouds of interstellar matter, and possibly rogue planets or stellar remnants. Most encounters will be minor. A slight tug on the Oort cloud. A tiny shift in planetary orbits too small to measure. Occasionally, something more significant occurs. A star passes within a light year, scattering comets inward. A molecular cloud drifts through the system, altering solar radiation through increased dust. A massive object transits nearby, pulling planets into new configurations. These are not hypothetical scenarios invented to frighten people. They're documented processes observed in other stellar systems and predicted by our understanding of galactic dynamics. We exist in a galaxy that doesn't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. Acknowledging this doesn't mean giving up. It means recognizing which problems require solutions and which require acceptance. We can't prevent stellar encounters. We can understand them, model them, and perhaps detect them earlier with better observation networks. That knowledge serves a purpose even if it doesn't change outcomes. Human time operates on scales measured in decades or centuries. Stellar mechanics operate on scales measured in millions of years. That disconnect creates a perceptual problem. We evolved to recognize immediate threats. Predators, storms, drought. Our nervous systems weren't built to process dangers that unfold over timeframes longer than civilizations exist. A star passing within 2 light-years over the next million years doesn't trigger the same response as something happening next week. But the physics doesn't care about our perception. Gravity operates continuously. Orbits shift gradually. What seems stable on human timescales reveals itself as dynamic when viewed across proper intervals. Jupiter's orbit changes. Saturn's rings evolve. The Moon recedes from Earth at about 4 centimeters per year. These aren't static objects frozen in place. They're participants in an ongoing gravitational negotiation that never stops. Now scale that up to galactic levels. The Milky Way contains 200 billion stars, most with their own planetary systems. Add brown dwarfs, rogue planets, stellar remnants, molecular clouds, and regions of concentrated dark matter. Everything moves. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion, where encounters between systems happen regularly across cosmic timescales. Our Sun orbits the galactic center once every 230 million years. During each orbit, it passes through different regions of the galaxy. Spiral arms, interarm regions, areas of higher and lower stellar density. Each environment presents different risks. Spiral arms contain more massive stars, which means more supernovae, more stellar winds, more radiation. They also contain giant molecular clouds that can trigger ice ages by blocking sunlight. Interarm regions are quieter but not empty. Rogue objects drift through these spaces. Stellar remnants. Planets ejected from their original systems. Objects too dim to detect until they're relatively close. The galaxy doesn't maintain clear boundaries between safe and dangerous zones. It's all dangerous given enough time. What varies is the probability and severity of encounters. Right now, the solar system occupies a relatively calm neighborhood. The nearest star, Proxima Centauri, sits 4.2 light-years away. That's far enough that its gravitational influence on our planets is negligible. The next closest stars are also comfortably distant. This configuration is temporary. Stars move at different velocities relative to each other. In about 30,000 years, a red dwarf called Ross 248 will pass within 3.2 light-years of the Sun, becoming our closest neighbor for a time. Then it will continue on its path and something else will take its place. These close passes happen regularly on galactic timescales. Most are harmless. A star passing within 5 light-years exerts minimal gravitational influence on planets orbiting another star. The effects are measurable in simulations but negligible in practice. Closer encounters are rarer but more consequential. A star passing within 1 light-year would perturb the Oort cloud significantly, potentially sending comets into the inner solar system for millions of years afterward. A star passing within half a light-year could affect planetary orbits directly, though the changes would be subtle unless the encounter was extremely close. The problem is detection. We can track nearby stars with current technology, but only the relatively bright ones. Dim red dwarfs, brown dwarfs, and rogue planets are much harder to spot until they're already close. Infrared surveys have improved our ability to find these objects, but gaps remain. Something could be approaching that we won't notice until it's within a few light years. By then, we'd have thousands of years to study it but no ability to change its trajectory. Altering the path of a stellar mass object would require energy expenditures far beyond anything human technology can produce. You can't nudge a star the way you might deflect an asteroid. The mass difference is too large. The energies involved too extreme. Even if we had millions of years to prepare, the engineering challenges would be insurmountable. Which brings us back to the same conclusion. Observation and understanding, yes. Prevention, no. We can map nearby space. We can identify potential threats decades or centuries before they arrive. We can calculate exactly what will happen during an encounter. None of that changes the outcome. It just means we'll know what's coming. There's value in that knowledge even without the ability to act. Understanding allows for preparation of a different kind. Not physical defenses, but intellectual frameworks. If we know a stellar encounter will destabilize the Oort cloud in 50,000 years, that information becomes part of how future generations think about long-term survival. Maybe it influences where deep space probes are sent. Maybe it affects how astronomical databases are maintained. Maybe it does nothing practical but satisfies the human need to understand our environment. That need is real even when it doesn't lead to solutions. We study supernovae knowing we can't prevent them. We model black hole behavior knowing we'll never interact with one. We map the cosmic microwave background knowing it tells us about events we can't influence. Knowledge has value independent of utility. Stellar encounters fall into that category. They're important to understand because they're part of the environment we exist in. They shape planetary evolution. They influence the long-term habitability of solar systems. They determine which configurations of planets remain stable over billions of years. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. A distant encounter might scatter some comets. A close encounter could reshape orbits. An extremely close encounter could eject planets from the solar system entirely. These aren't equally likely. The probability decreases dramatically as encounters get closer. But over billions of years, even low-probability events become near certainties. The Sun will experience multiple close encounters before it exhausts its hydrogen fuel. Some will be minor. At least one might be significant. The galaxy guarantees change over sufficient timescales. What it doesn't guarantee is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, the system reorganizes into a new stable state that might look nothing like the original. This has already happened to countless other systems. We observe planetary systems with highly eccentric orbits, planets too close to their stars, gas giants in locations where they couldn't have formed. These are signatures of past disruptions. Encounters with other stars. Planetary migrations triggered by gravitational interactions. Systems that reorganized after their original configurations became unstable. Our solar system shows signs of its own past reorganization. The NICE model suggests that Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions. They migrated inward and outward after formation, possibly triggered by encounters with planetesimals or resonances between their orbits. This migration would have scattered smaller bodies throughout the solar system, explaining features like the late heavy bombardment 4 billion years ago. If that model is correct, the solar system has already experienced major gravitational reshuffling. What we see now is the result of that reorganization, not the original configuration. Which means change isn't hypothetical. It's already happened. The question is whether it will happen again during the remaining lifespan of the Sun. Probability suggests yes. Timing remains unknown. The galaxy contains too many variables to predict specific encounters far in advance. We can calculate general probabilities. We can identify nearby objects and track their movements. We can model what would happen under different scenarios. What we can't do is point to a specific date and say this is when the next major disruption occurs. That uncertainty is permanent. It's built into the nature of galactic dynamics. Too many objects moving in too many directions with too many possible interactions. Even perfect knowledge of current positions and velocities wouldn't allow precise predictions millions of years ahead because gravitational interactions are chaotic. Small changes in initial conditions produce large differences in outcomes over time. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. The math doesn't allow exact long-term predictions even in principle. We're left with statistical models and probability ranges. Useful for understanding general patterns but useless for predicting specific events. That's not a limitation of current technology. It's a fundamental feature of how gravity works in systems with multiple interacting masses. Chaos isn't something better computers can solve. It's an inherent property of the equations governing motion. Which means we'll never have certainty about future stellar encounters. We'll have better observations, more detailed models, improved probability estimates. We won't have schedules. The galaxy doesn't operate on schedules. It operates on physics, which produces patterns but not predictability. Stars move through space according to gravitational laws that allow probability calculations but resist precise forecasting over timescales measured in millions of years. The Sun's journey through the galaxy has already lasted 4.5 billion years. During that time, it's completed roughly 20 orbits around the galactic center. Each orbit takes between 200 and 250 million years, depending on the Sun's exact distance from the center and the distribution of mass in the galaxy. 20+ complete circuits means 20+ passages through the spiral arms, dozens or hundreds of close encounters with molecular clouds, and countless interactions with the changing gravitational landscape of the Milky Way. The solar system survived all of it. The planets remained in stable orbits. Earth maintained conditions suitable for life across geological timescales. Whatever encounters occurred during those billions of years, none were catastrophic enough to eject planets or sterilize Earth. That's not luck. It's statistics. Most stellar encounters are distant enough to cause minimal disruption. The dangerous ones are rare. Over billions of years, the rare events that do occur tend to fall within a range the system can absorb without complete destruction. But survival of past encounters doesn't guarantee immunity from future ones. Each passage through a spiral arm resets the probability. Each orbit through the galaxy exposes the Sun to new potential interactions. The gravitational environment changes constantly as stars move through their own orbits, clusters form and dissolve, and the galaxy's structure evolves. What protected the solar system during previous orbits might not be sufficient during future ones. The distribution of stars changes. Regions that were once relatively empty can become more crowded as stellar populations shift. The Sun's current path through the galaxy might take it through denser neighborhoods than it experienced in the past. Or it might lead it into quieter regions. There's no way to know without detailed mapping of stellar trajectories across millions of years, which remains beyond current observational capabilities. One factor that does influence encounter probability is the Sun's vertical oscillation through the galactic plane. The Sun doesn't orbit the galactic center in a flat circle. Its path carries it above and below the galactic plane in a wave-like motion, crossing through the plane approximately every 30 to 40 million years. When the Sun passes through the galactic plane, it encounters higher stellar densities than when it's above or below. The plane contains most of the galaxy's visible matter, including stars, gas, and dust. Crossing through it increases the probability of close encounters simply because there are more objects present. Some researchers have suggested this oscillation might correlate with mass extinction events on Earth, proposing that encounters with molecular clouds or increased comet impacts occur more frequently during plane crossings. The evidence remains debated. Extinction patterns don't show clear periodicity matching the oscillation cycle. Even if a correlation exists, it would demonstrate that galactic position influences Earth's history, not that future crossings will necessarily produce similar effects. Each crossing involves different molecular clouds, different stellar configurations, different gravitational contexts. Past patterns don't predict future outcomes with certainty. Beyond stellar encounters, the Sun faces long-term changes in the galaxy's overall structure. The Milky Way is currently on a collision course with the Andromeda Galaxy. The two galaxies will begin interacting in approximately 4 billion years, with a full merger occurring over the following few billion years. During galactic mergers, stellar orbits get disrupted on massive scales. Stars that once followed predictable paths around their galactic centers get scattered into new configurations as the two galaxies' gravitational fields interfere with each other. The Sun will likely survive the merger physically. Galactic mergers don't involve stars actually colliding because the distances between stars are enormous compared to their sizes. Even when two galaxies interpenetrate completely, the probability of any given star hitting another star remains vanishingly small. What changes is orbital structure. The Sun's current orbit around the Milky Way's center will become meaningless as that center merges with Andromeda's center. The combined galaxy, sometimes called Melkomena, will have a different shape, different rotation, different gravitational architecture. The Sun will end up in a new orbit around the merged galaxy's center, potentially far from its current position. That repositioning might place the Sun in denser regions with higher encounter probabilities, or in sparser regions with lower probabilities. The outcome depends on details of the merger that can't be predicted precisely. Simulations show general patterns but can't specify where individual stars end up. Too many variables. Too many gravitational interactions occurring simultaneously. The merger timeline presents an interesting coincidence. 4 billion years from now, the Sun will be nearing the end of its main sequence lifetime. It will have exhausted most of its hydrogen fuel and begun transitioning toward the red giant phase. The Andromeda merger will commence around the same time the Sun starts expanding. Earth's fate might be sealed by solar evolution before galactic dynamics become the dominant concern. As the Sun expands into a red giant, it will engulf Mercury and Venus. Whether it reaches Earth's orbit remains uncertain and depends on exact mass loss rates during the expansion. Even if Earth's orbit isn't physically consumed, the increased solar radiation will vaporize the oceans and strip away the atmosphere long before the Sun's surface reaches Earth's position. By the time the galactic merger creates new gravitational dynamics, Earth will likely already be uninhabitable. That doesn't mean stellar encounters before then are irrelevant. Between now and the Sun's red giant phase, roughly 5 billion years remain. During that time, the Sun will complete another 20 orbits around the galaxy. 20 more passages through spiral arms. Hundreds more opportunities for close encounters. The probability that at least one significant encounter occurs during those 5 billion years is not negligible. What constitutes a significant encounter? Definitions vary depending on what effects you're measuring. For disrupting the Oort cloud and potentially triggering comet showers, encounters within 1 or 2 light years matter. For perturbing planetary orbits directly, encounters need to be much closer, probably within a few thousand astronomical units. For ejecting planets entirely, encounters likely need to approach within hundreds of astronomical units. Each category has different probabilities and different consequences. Oort cloud disruptions are relatively common on million-year timescales. Direct planetary perturbations are rare but not impossible. Planetary ejections are extremely rare but have definitely occurred in other systems. The solar system probably won't experience a catastrophic close encounter during the next billion years. Probably. That's the strongest statement physics allows. The galaxy doesn't provide guarantees. Observation programs continue tracking nearby stars, measuring their positions, velocities, and trajectories. As data accumulates, predictions improve for specific stars over limited time periods. Gliese 710 will pass within 10,000 astronomical units in about 1.3 million years. HIP 85605 might come within 16,000 astronomical units in 240,000 years. These predictions carry uncertainty margins that increase with distance into the future. A star projected to pass at 10,000 astronomical units might actually pass at 8,000 or 12,000 depending on factors not fully constrained by current measurements. The difference matters when calculating gravitational effects on the Oort cloud. Small changes in closest approach distance produce large changes in the number of comets perturbed. Even with improving data, predictions beyond a few million years remain probabilistic rather than deterministic. The galaxy contains too many objects with too many possible interactions. The Sun's journey through the galaxy continues. Right now, it's moving toward the constellation Hercules at roughly 250 kilometers per second relative to the local standard of rest. That motion carries it through neighborhoods where stellar densities fluctuate, molecular clouds drift, and gravitational influences shift. Over the next 100 million years, the Sun will move several thousand light-years from its current position. New stars will become neighbors. Current neighbors will drift away. The gravitational landscape surrounding the solar system will transform completely multiple times before the Sun exhausts its hydrogen fuel. Each transformation brings new encounter possibilities. Each possibility carries a probability that can be calculated but not eliminated. The galaxy guarantees that change happens. It doesn't specify when or how severely. Our solar system exists in a dynamic environment where stability is temporary and disruption is eventual. Not immediate. Not predictable in detail. But inevitable given sufficient time. That's the nature of gravitational systems with many interacting bodies moving through space. Chaos emerges from deterministic laws. Probability replaces certainty. Patterns appear but predictions fail beyond certain timescales. The Sun will continue orbiting the galactic center, crossing through spiral arms, oscillating above and below the galactic plane, encountering molecular clouds and passing stars. Most encounters will be distant and inconsequential. Some will perturb the Oort cloud and send comets toward the inner solar system. A few might disturb planetary orbits enough to measure. One might eventually be close enough to fundamentally alter the solar system's architecture. We can't prevent it. We can't predict exactly when it will happen. We can only observe, calculate probabilities, and understand that the galaxy operates on timescales where rare events become commonplace. The question isn't whether the solar system will experience future disruption. The question is whether it will happen during a time frame that matters to us. For the next few million years, probably not. Beyond that, certainty dissolves into probability, and probability suggests that eventually, something significant will occur. The galaxy has 400 billion stars moving through space. The Sun is one of them, following its orbit through a constantly shifting gravitational landscape. Every orbit brings new encounters. Every encounter carries probabilities. Given enough orbits, those probabilities converge toward inevitability. That's not pessimism. That's mathematics applied to gravity operating across billions of years in a galaxy that never stops moving. The galaxy we inhabit operates without regard for our presence. Rogue black holes drift through the darkness between stars, following paths set by violent births millions or billions of years ago. Hundreds of millions of them, perhaps more, scattered across the Milky Way like invisible landmines in a cosmic ocean. We've detected a handful. The rest remain hidden, detectable only through rare gravitational lensing events that require perfect alignment and extraordinary luck. Detection methods improve. Surveys expand. Observation networks grow more sophisticated. None of it changes the fundamental problem. We're looking for objects that emit no light, produce no radiation, and reveal themselves only by bending the light of background stars during brief windows of alignment. Even when we catch these events, we're seeing something that happened years or centuries ago. The black hole itself has already moved on, continuing along a trajectory we can't predict with useful precision. The mathematics of galactic dynamics allows probability calculations but resists exact forecasting. Too many objects moving in too many directions with too many possible interactions. Free body problems are analytically unsolvable. Stellar neighborhoods involve millions of bodies. Chaos emerges from deterministic laws. Small changes in initial conditions produce wildly different outcomes over time. We can model general patterns but can't predict specific encounters millions of years ahead. That uncertainty is permanent. It's built into how gravity works in systems with multiple interacting masses. Better observations won't fix it. More powerful computers won't solve it. The galaxy doesn't operate on schedules we can map. It operates on physics that produces patterns but not predictability. What matters is understanding our position within this dynamic system. The solar system exists in its current configuration because nothing has disrupted it recently. That's not a permanent state. It's a temporary snapshot of one moment in an ongoing process that operates on timescales longer than human history but shorter than planetary lifespans. Change is guaranteed over sufficient time. What isn't guaranteed is survivability. Systems that get disrupted don't recover their original configurations. Planets that get ejected don't return. Once gravitational chaos reaches a certain threshold, everything reorganizes into a new stable state that might look nothing like what came before. This has happened to countless other systems. We observe the signatures in eccentric orbits, misplaced planets, and configurations that couldn't have formed naturally. Evidence of past encounters that reshaped entire solar systems. Our own system shows signs of reorganization in its past. the planets might not occupy their original positions. The late heavy bombardment 4 billion years ago suggests major gravitational reshuffling occurred. What we see now could be the result of that ancient chaos, not the initial arrangement. Which means change isn't hypothetical. It's already happened here. The question is whether it will happen again on timescales that matter to anything currently alive. Probability suggests yes, eventually. Timing remains unknown. The Sun will experience multiple close encounters with other stars, molecular clouds, and possibly rogue black holes before it exhausts its hydrogen fuel. Most will be minor. Some might be significant. One could potentially be catastrophic. The galaxy guarantees encounters over billions of years. It doesn't specify which ones will matter or when they'll occur. We can't defend against threats operating at stellar scales. We can't deflect a black hole or alter the trajectory of a passing star. The mass differences are too large. The energies involved too extreme. Even with millions of years to prepare, the engineering challenges would remain insurmountable. You can't nudge a stellar mass object the way you might deflect an asteroid. What we can do is observe, understand, and acknowledge which problems exist outside our ability to solve. Knowledge has value independent of utility. We study phenomena we can't influence because understanding our environment matters even when we can't control it. Rogue black holes are part of that environment. They shape galactic evolution. They influence which planetary configurations remain stable over billions of years. They determine, in ways we're only beginning to understand, which systems survive long enough for complex life to develop. Earth exists in its current form partly because the solar system hasn't experienced a major gravitational disruption since planets finished forming. That stability allowed life to develop, evolve, and eventually produce technological civilization. It's not guaranteed to continue. At some point, something will pass close enough to change things. When that happens, the consequences depend entirely on what passes and how close it gets. The galaxy contains 400 billion stars moving through space, countless stellar remnants, molecular clouds, rogue planets, and objects we haven't cataloged yet. Everything pulls on everything else within its gravitational influence. The result is a galaxy in constant motion where encounters between systems happen regularly across cosmic timescales. Most are harmless. Some aren't. The difference comes down to distance, mass, velocity, and timing. Variables we can measure in nearby objects but can't predict far in advance for the galaxy as a whole. So we exist in a dynamic galaxy where invisible predators drift through the darkness, occasionally reshaping solar systems they pass near. We have no systematic way of knowing where most of them are or where they're going. The best we can do is understand the physics, recognize the risk exists, and accept that some threats operate on scales beyond human ability to address. That acceptance isn't fatalism. It's recognition of what we can and can't control, and focusing effort on things that actually matter within our capability to influence. The galaxy operates according to physical laws that don't care about preserving any particular arrangement of matter. Stars form, evolve, and die. Planets coalesce and get destroyed. Systems reorganize under gravitational influences that operate without regard for what lives on them. We're participants in that process, not exempt from it. Understanding that doesn't change outcomes. It just means we'll know what we're looking at when the galaxy reminds us that stability is always temporary.